In this video, we're going to look at higher degree polynomials and their graphs. When we refer to a higher degree polynomial, we're talking about a polynomial of degree 2 or higher than 2. We want to be able to take a look at these graphs from standard form and linear factorization form or just factored form. Standard form, an example here would be 2x to the fourth minus 3x squared plus 7x minus 10. We want to be able to identify a couple things in here. So a sub 0 is my y-intercept, so your constant is going to be your y-intercept. A sub n is your leading coefficient, so the number in front of your highest degree term is your leading coefficient. And then our highest exponent is going to be our degree. So my degree. So this polynomial example that I gave here is a polynomial of degree 4. The leading coefficient is 2, and the y-intercept would be negative 10. From our second example, the linear factorization form, again, I still have my leading coefficient, so the negative 3 is going to be my leading coefficient. And then from the factored form, what we can get are our zeros. So from this equation here, we should know that I have zeros at x equal 4, negative 2, and positive 6. The sign of my leading coefficient is going to tell me whether my graph opens up. So my graph is going to open up when my leading coefficient, so a sub n, is greater than 0, or it's going to open down, and this would occur when my leading coefficient is less than 0. Every polynomial function is going to have exactly one y-intercept. Remember, in standard form, I can find it right away because it's my constant. In factored form, we would have to plug in 0 to find that leading coefficient. Okay, so looking at the zeros of a function, we want to be able to find a zero of a linear function, a quadratic function, and a polynomial function from factored form. So remember that a 0 is any value which when I plug it into the function will evaluate to 0. Also, if that 0 is a real number, then it is also an x-intercept. Zeros can be complex numbers. X-intercepts cannot be complex numbers, so x-intercepts can only be real numbers. So looking at our first example here, this is just a linear function, 3x minus 6, so I'm just going to set that equal to 0, and when I solve that, I'm going to get x equal 2. So that means I have a 0 at x equal 2. Since that's a real number, that's also an x-intercept, so then I have an x-intercept at the point 2, 0. In the second example, now I have a quadratic function. So here I'm going to have x squared minus 4 equals 0. We have lots of ways to solve a quadratic, so it doesn't matter how you do it. I'm just going to extract the roots on this one. So I'm going to get x equals plus or minus 2. So this tells me I have zeros at x equals negative 2 and positive 2. Both of those are real numbers, so I have two x-intercepts at the points negative 2, 0 and positive 2, 0. In this last example, we have a polynomial in factored form. So remember here, we just set each factor equal to 0 and solve it. So I'm going to go x minus 1 equals 0, which is going to give me x equals 1. I have x minus 2i equals 0, so that's going to give us x equals 2i. And finally, we have x plus 2i equals 0, which is going to give us x equals negative 2i. So I have three zeros at x equals 1, 2i, and negative 2i. Remember, x-intercepts can only be real numbers, so I have x-intercept at the point 1, 0. 2i and negative 2i are not real numbers, so they do not count as x-intercepts. So that graph has only one x-intercept. We also want to be able to discuss the multiplicity of a 0. So the multiplicity of a 0 is simply the degree on that factor from factored form. A factor of a polynomial is any term that contains a variable. So if you have a leading coefficient, it does not represent a factor. It's just the leading coefficient. If a factor doesn't have an exponent, then it's 1, and its multiplicity is also 1. And when my multiplicity is an odd value, then we know that it crosses through the axis. When the multiplicity is an even value, then we know that it just touches the axis, creates a maximum or a minimum point. So again, working from factored form, we want to be able to find the zeros and the multiplicities. So in this first example, I have 3. That's my leading coefficient, so it doesn't affect my zeros or my multiplicities. Next, I have x minus 6, so I'm going to set the x minus 6 equal to 0, and I get x equals 6. The exponent here would be a 1, so my multiplicity, we're going to use capital M to represent multiplicity as 1. Next I have x plus 2 squared, so I'm going to take the x plus 2, set that equal to 0. I get x equals negative 2. The multiplicity on that is going to be 2. So I had x equals 6 right here, and that had an odd multiplicity, so it's cutting through the axis. And then we had the negative 2 here, and that multiplicity was even, so it's just touching the axis. In my next example, I have x squared, so x equals 0, and that multiplicity is 2. So here's my x equals 0, and the multiplicity is 2, so we're just touching the axis at that point. Next I have x minus 4. So I'm going to set that equal to 0, so we get x equals 4, and then the exponent on that is 3, so my multiplicity is 3. So here's my x equals 4. I'm cutting through the axis there because my multiplicity is odd. And then finally I have x minus 5 equals 0, so x equals 5, and my multiplicity on that again would be 1 because there's no exponent seen there, so we know that it's 1. So here I have x equals 5, and I'm crossing through the axis because of the odd multiplicity. On the last example, I have the negative 4. Remember, that's my leading coefficient. It doesn't affect my zeros or my multiplicities. Next, I have x minus 1 equals 0. So x equals 1, and my multiplicity there is 4. So here's my 1, and the multiplicity is even, so it's just touching the axis there. My next factor is x minus 2, so I'm going to set that equal to 0, so I get x equals 2, and my multiplicity would be 1. So we're cutting through the axis there because it's an odd multiplicity. And finally I have x plus 7 equals 0. So my 0 is at x equals negative 7, and my multiplicity is 1. So here's my x equals 7, and we're cutting through the axis because of the odd multiplicity. So now kind of working backwards, here we have the graph. We want to find the zeros and tell if the multiplicity is even or odd. I can't specifically give the multiplicity based on the graph, but I can tell if it's even or odd. So sort of moving across this graph from left to right, the first intersection I have with the x-axis is right here. So I have a 0 at x equals negative 5, and I know that my multiplicity is even there because we're just touching the axis. If we continue kind of tracing this graph, the next time that I intersect the x-axis, we've got x equals negative 2, and here we're crossing through the axis, so I know my multiplicity is odd. Continuing, the next time we intersect the axis is here at x equals 0, so I have a 0 at 0, and I know my multiplicity is odd because we're crossing through the axis there. My next 0 is going to be at x equals 3, and my multiplicity is even there because we're just touching the axis, creating a maximum or a minimum point. And finally, my last 0 that I can see here is x equals 6, and my multiplicity is going to be odd there because we're crossing through the axis. So finding zeros from standard form, we're going to use the calculator and use the graph. So we first want to graph it, and then we want to find the zeros either using 0 or intersection. Once I have that, I can identify my zeros, and then I can tell if my multiplicity, again, is even or odd. We can't specify the exact multiplicity, but we can tell if it's even or odd. So from this first graph, we had an intercept at negative 2.5, and that's crossing through the axis there, so I know that that multiplicity is odd. Also, from this graph, we can see that we have a 0 at negative 1. So I have a 0 at x equal negative 1. There I'm just touching the graph, so I know that my multiplicity is even. And then finally out here, we have a 0 at x equals 7, and my multiplicity would be odd there because I'm crossing through the axis. On the second graph, we had a 0 at x equals negative 2.3 repeating. I'm crossing through the axis there, so I know my multiplicity is odd. And then I have another 0 over here at x equals 3, and I'm touching the axis there, so my multiplicity is even. On this last example, we have a 0 at x equals negative 6.22, crossing through the axis there, so I know my multiplicity is odd. This other 0 over here is actually at positive 6.22. Remember, you can find those using 0 or intersection on your calculator. And again, I'm crossing through the axis there, so my multiplicity is going to be odd. Okay, so trying to pull all of this together, looking at a polynomial graph from the equation or backwards. If the leading coefficient is positive, then I know the right side goes up. If the leading coefficient is negative, then I know the right side goes down. If my degree is even, then the left and right sides go in the same direction, or you can think of this as equal directions. So even E, equal E. If the degree is odd, then my end behaviors go in opposite directions. So you have the alliteration to help you remember that there. So combining those two things together, if my degree is even and my leading coefficient is positive, then my end behaviors should be both going up. So both of these will be going to positive infinity. We don't really know what's happening in the middle of the graph here from the end behavior, so all we're concerned about is just the extremes, the limit to the left and to the right. If my degree is odd, but my leading coefficient is positive, then my end behaviors are going in opposite directions, and then the right side is going up. So again, we don't really know what's happening here, kind of connecting these together. But on the right side, I'm going to positive infinity. On the left side, I'm going to negative infinity. So remember, odd, they're going in opposite directions. Even, they're going in the same direction or equal directions. Down here, if my degree is even but it's negative, then they should both be going down. And then they would be connected together somehow, so they would both be going to negative infinity. And if it's odd and negative, so then the negative tells us that the right side's going down, and odd, they're going in opposite directions, so the other side's going to be going up. So here on the right side, I'm going to negative infinity, and on the left side, I'm going to positive infinity. Also, I have a few theorems that I can use here. So the maximum number of x-intercepts of the graph is the same as the degree of the function. The maximum number of x-intercepts of the graph is the same as the degree of the function. Now remember, this is the maximum number, so it could be fewer, but I cannot have any more x-intercepts than equal to my degree. The maximum number of extrema of the graph is equal to the degree minus 1. So 1 less than degree is the maximum number of x-intercepts, or extrema, that I can have. So this is a first degree polynomial. I have 1, 0, or 1 x-intercept, and no extrema. This is a degree 2 polynomial. So I have 2 x-intercepts, and I have 1 maxima, or 1 extrema. This is a degree 3 polynomial. So we have 3 x-intercepts. Oh my God. Okay, so trying to pull all of this together, looking at a polynomial graph from the equation or backwards. If the leading coefficient is positive, then I know the right side goes up. If the leading coefficient is negative, then I know the right side goes down. If my degree is even, then the left and right sides go in the same direction, or you can think of this as equal directions. So even E, equal E. If the degree is odd, then my end behaviors go in opposite directions. So you have the alliteration to help you remember that there. So combining those two things together, if my degree is even and my leading coefficient is positive, then my end behaviors should be both going up. So both of these will be going to positive infinity. We don't really know what's happening in the middle of the graph here from the end behavior, so all we're concerned about is just the extremes, the limit to the left and to the right. If my degree is odd, but my leading coefficient is positive, then my end behaviors are going in opposite directions, and then the right side is going up. So again, we don't really know what's happening here, kind of connecting these together. But on the right side, I'm going to positive infinity. On the left side, I'm going to negative infinity. So remember, odd, they're going in opposite directions. Even, they're going in the same direction or equal directions. Down here, if my degree is even but it's negative, then they should both be going down. And then they would be connected together somehow, so they would both be going to negative infinity. And if it's odd and negative, so then the negative tells us that the right side's going down, and odd, they're going in opposite directions, so the other side's going to be going up. So here on the right side, I'm going to negative infinity, and on the left side, I'm going to positive infinity. Looking at a few more properties of polynomial functions, I want to look at maximum number of extrema and maximum number of x-intercepts. So here I have a linear function, which is degree 1. So no matter what I do to this line, if I move these points around, I continue to have always one x-intercept and no extrema. Taking a look at a second degree function, right now we have 2 x-intercepts as noted by the red dots, and I have 1 extrema point here. So again, if I kind of move some of these points, I can change this so I have no x-intercepts. I could change this so I have 1 x-intercept. This one would be right here on the axis. So 0 x-intercepts, 1 x-intercept, 2 x-intercepts. And there's nothing I can do to change the number of extrema. No matter what I do to this parabola, I have 1 extrema point. Looking at a third degree polynomial, right now I have 1 x-intercept. If I kind of change this a little bit, I can get 2 x-intercepts. I can continue down, I get 3 x-intercepts. I can't get any more than that, so this third degree polynomial is a maximum number of 3 x-intercepts. Here I have 2 extrema points. I have a local max here and a local min here. So I can kind of change this a little bit. I can change the graph so I have no extrema. This would be constantly increasing, or I can change this so I have 2 extrema. So because my graph is going from negative infinity to positive infinity, if I have 1 extrema, I have to have 2 so that I can change directions again. So here I have at most 3 x-intercepts. At most 3 x-intercepts, and also at most 2 extrema. So I can either have 2 extrema or 0 extrema. I can't have 1 extrema here because then I would not be able to change direction again. Lastly, I have a fourth degree polynomial. This one has 4 x-intercepts right now. Again, I can kind of change this graph. So now I've got 2 x-intercepts. I can pull this down right here on the axis. I have 3 x-intercepts. I can move this all the way up. So I have 1 x-intercept here, or I can move it all the way up so I have no x-intercepts. So here I could have 0, I could have 1, I could have 2, and then I can change this so I can have 3 right here and also 4, but I can't get any more than 4. Right now I have 3 extrema. I have 2 local, or 2 absolute min, a local min, and a local max. Again, I can change this so I have 1 extrema. So I can have 1 extrema, or I can have 3 extrema. I can't have 2 extrema because that would ruin the end behavior of my graph. So if we come back here to our information, so the maximum number of x-intercepts of the graph is the same as the degree. And the maximum number of extrema of the graph is the same as the degree minus 1. So 1 less than the degree. What we want to be able to do here is take a look at this equation. We want to be able to find the zeros and the multiplicities, whether or not it's going to cross the axis, give the degree of the function, the end behavior of the function, the maximum number of extrema, and then give a general sketch of the graph. So we're going to start with here my zeros. So I'm going to get my zeros from this factored form. So I have a 0 at x equals 0. Its multiplicity is 3 there. So that's odd. So that means it's crossing through the axis. Next I have x minus 2 equals 0, so that's going to give me x equals 2. My multiplicity there is even 2, so that means it just touches the axis. And finally I have x plus 6, so x equals negative 6. My multiplicity there is going to be 1, which is an odd number, so it's going to cross through the axis. The degree of my polynomial is the sum of my multiplicities, so we've got 3 plus 2 plus 1, which gives me 6. So my degree is 6, which is even, which tells me that my end behaviors are going in the same direction. And my leading coefficient is negative 8, which is negative. So that means the right side goes down. Since my degree is even, they're going to go in equal or the same direction, so that means the left side also goes down. And then my maximum number of extrema is going to be 1 less than my degree, so 6 minus 1 equals 5. Finding the y-intercept, we're just going to plug 0 in for x, so we're going to do f of 0. So we have negative 8 times 0 cubed times 0 minus 2 squared times 0 plus 6 to the first power, which is going to give me negative 8 times 0 times negative 2 squared times 6, which is just going to give me 0. So now to do a general sketch of this graph, the first thing I'm going to do is mark my x and y intercepts. So remember, I have an x-intercept at 0, I have an x-intercept at positive 2, and I have an x-intercept at 6, negative 6. My y-intercept is also 0, so that point is already noted on there. Next, you're going to draw in your end behaviors. Both of your end behaviors are going down. So from the left and rightmost extreme or x-intercepts, I'm going to draw that down. Then we're going to connect the x-intercepts together, making sure to cross and touch the axis appropriately. So negative 6, we cross through the axis, so I'm going to come up, and then at 0, I'm going to cross through the axis again, so I'm going to go all the way down. And then at the 2, I'm just going to touch the axis, so we're just going to hit a little maximum point there. And then you have a general description of your graph. It's not an accurate graph, but it's a general sketch of the graph. So now to do a general sketch of this graph, the first thing I'm going to do is mark my x and y intercepts. So remember, I have an x-intercept at 0, I have an x-intercept at positive 2, and I have an x-intercept at 6, negative 6. My y-intercept is also 0, so that point is already noted on there. Next, you're going to draw in your end behaviors. Both of your end behaviors are going down. So from the left and rightmost extreme or x-intercepts, I'm going to draw that down. Then we're going to connect the x-intercepts together, making sure to cross and touch the axis appropriately. So negative 6, we cross through the axis, so I'm going to come up, and then at 0, I'm going to cross through the axis again, so I'm going to go all the way down. And then at the 2, I'm just going to touch the axis, so we're just going to hit a little maximum point there. And then you have a general description of your graph. It's not an accurate graph, but it's a general sketch of the graph.